All right, so we finished last time talking about this thing that happened when I had the weights on the chair and I was spinning around, and it seemed to make me go faster when I pulled them in. We talked a bit about central forces and how that works, and how the force that I applied on the weights when I was pulling them towards me, how those were central forces and how they don't exert any torques, and thus how angular momentum is conserved because there were no external torques, no internal torques, no nothing. And so that would imply that if my moment of inertia decreased, in order to compensate, because the angular momentum is the same, my angular velocity has to increase. And so that's what caused the increase in my angular velocity. That's why I sped up when I pulled the weights inwards. We're going to talk about this in a little bit more detail, do some actual mathematical analyses of this so we can better understand. So it doesn't really have a formal name, but I like to call it the ice skater effect, because you've all seen videos or GIFs of ice skaters doing this sort of thing. So I'm going to do what physicists do, and I'm going to give you a simplified model of the ice skater effect. So instead of an ice skater, we have a disk spinning about some axis. And instead of arms and weights, we just have a point mass that is sitting somewhere near the edge of the disk, mass m. That distance, we'll call it r. And the ice skater, the disk, is initially spinning around our axis with some initial angular velocity omega I. Now this is the before picture, before the ice skater pulls in the weight. Afterwards, after pulling to the center, the picture looks something like this. Let me copy this just so it looks approximately the same. Now, all of that point mass m is at the edge, or it is in the middle, and it might have a new speed. In fact, it does have a new speed. That's what I showed you guys last time. So in this case, imagine me as the disk, the point mass as the weights. It doesn't matter which side they're on, it's all the same. And so we can actually do some calculations now. So I'm just going to assume that this disk has some moment of inertia I, which is separate from the point mass. It just is what it is. Now, you could, maybe it's the moment of inertia of me in the chair, maybe it's the moment of inertia of the ice skater, whatever. It's just something. It's just some positive number. So because the angular momentum is conserved, because there's only a central force which causes no torque, it's useful to apply that angular momentum to try to learn about the system. So let's write down what the initial angular momentum is. Now keep in mind, I'm just going to be writing down the magnitude of the angular momentum. Remember, it's typically a vector, but I'm just going to write down the magnitude because we know what direction it's in. We can use the right-hand rule, and we would find that it points upwards, right? So just because, well, yeah, it would point upwards on the screen, but don't pay attention to the, I'll even just draw a vector. Up. And similarly, because the angular momentum is conserved, the final angular momentum should also point upwards. So the reason why we can work with just the magnitude is because the direction doesn't change. Right, so the initial angular momentum would be the initial moment of inertia of the whole system times the angular velocity of the whole system. It's all rotating as one body. So that means that we can just combine it into a total moment of inertia and a total angular velocity. Now, the moment of inertia of the whole system about this axis, about this central axis here, would be the moment of inertia of the disk about that central axis plus mr squared. Now, the reason why it's mr squared is because this is a point mass on the edge here. And for a point mass, the moment of inertia is always just the mass times the distance to the axis of rotation squared. That just is the moment of inertia of a point mass. And then the initial angular velocity is just whatever it is. It's omega I. Now we can do the same thing for the final moment of inertia. Now the final moment of inertia is the final angular momentum is again the final moment of inertia times the final velocity, angular velocity. But in this case, the point mass, because it's located at the center, at the axis of rotation, this term goes to 0. The distance that it is from the axis of rotation is 0. So this is just equal to I, which is the moment of inertia of the disk, times omega f. And so because the angular momentum is conserved, what we're left with is that Li has to equal Lf, right? And so we can just write this out. So we have I omega I squared, or not squared, sorry, plus mr squared omega I equals I omega f. And then we can solve for omega f in terms of omega I. Omega f is equal to 1 plus mr squared divided by I times omega I. So it's not a hard calculation. It's just angular momentum conservation. But what we learn is that the final angular velocity, omega f, is strictly greater than the initial angular velocity, omega I. And that's because it's omega I plus a little bit more times omega I. And we know that that's a positive number because angular moment, or because moment of inertia is always positive, mass is always positive, and radius squared is always positive. So this number is strictly bigger than 1. So you take whatever the initial angular velocity was, multiply it by whatever this number is, which is strictly bigger than 1, you get a new final angular velocity, and so it's bigger than the initial angular velocity. Now, that's all fine and dandy, but it seems kind of weird that the speed can just increase out of nowhere. So it's actually worth thinking about this a little bit more. Let's investigate what the kinetic energy of the system is. Because we know when the speed increases, the kinetic energy increases as the square of the speed. Not necessarily. The moment of inertia can be changing over time. You will only deal with problems that you have the tools to deal with, though. So let's write down. So by the way, in this situation, we would expect, we would not necessarily expect that the energy is conserved, right? There's no potential energies involved, but there is a force. In particular, there's a force where there's a force acting on the point mass, pushing it towards the center. So there could potentially be some external work that's being done. Like imagine that the ice skater isn't bringing it in, but like some external person is pushing the weight towards them. You could imagine that is work that's done, and so the kinetic energy might not be conserved. So let's write down what the kinetic energies are and see what happens. So the kinetic energy, this is rotational motion, and there's no translational motion, so it's just 1/2 times I omega squared. So in this case, it's 1/2 times the moment of inertia in the initial situation, I plus mr squared, times the initial angular velocity, omega sub I squared. The final kinetic energy, it's 1/2 I omega squared again, but this time the formula is slightly different. So it's 1/2 I, because the moment of inertia in the final situation is just the moment of inertia of the disk, but the speed here is different. The angular velocity, or the angular speed, is given in terms of omega sub I as this thing, this whole thing. So it's 1 plus mr squared over I, all squared, times omega sub I squared, right? All I did was I substituted in what omega f is, the final angular velocity, and then squared it. So we can take the difference of these two kinetic energies to figure out what the change in kinetic energy would be. The change in kinetic energy, just by subtracting final minus initial, is 1/2 mr squared times 1 plus mr squared over I times omega I squared. And again, importantly, this is greater than 0. Omega I squared is greater than 0. The stuff in parentheses is greater than 0. 1/2 mr squared is greater than 0. So the point is that the kinetic energy of the system increased. Now this seems strange because we know that maybe it doesn't seem strange, but I'll tell you why it's strange. So this whole problem is a rotational problem, right? It seems like if there's going to be any work that's done, it will be work done by a rotational force, by a torque, right? And then you would find that, work is the integral of tau d theta. But what we talked about last time is that actually the force that's applied on this point mass is a force that's pushing it towards the center of the circle. And when that happens, that would be what's called a central force. And we know central forces don't apply torques. So it cannot be the case that this extra energy came from rotational work. Because there's no torque. So where did it come from? Sorry, torque is equal to 0. So the only other place it could come from is via some sort of linear work, right? Work done by some linear motion. And maybe that was the obvious thing to begin with anyway, because while the whole thing is rotating, you're actually just pushing on the mass in a single direction, right? So let's examine the linear work that's done. Let's think about that a little bit. So if this is the mass, just isolating the point mass m, the force that's acting on it is a force that's something like, and maybe it's in the initial configuration, it's say a pulling or a pushing force that's pulling it towards the center. And so we know that there has to be a force on it to begin with, right? There has to be a force on it to begin with because the like before it's even pulled in, there has to be a force on it. And the reason for that is just because it's undergoing circular motion. And we know that circular motion implies there's an acceleration. And if there's an acceleration, there must be a force, right, from Newton's second law. So there must be some sort of force that's keeping it moving in a circle. But if we want to move it in an ever decreasing circle, this force that we act on, or this force that we're acting with, has to be slightly greater than the magnitude of the force that was there just to keep it in place. Has to be slightly greater. If it was equal to the centripetal, it's not centripetal force, no. So there was a force that was causing centripetal acceleration. There was a force that was causing the centripetal acceleration, keeping the object moving in a circle. But we're applying an additional force, like a pulling force that the ice skater or that I apply. That extra force, or rather the net force, I should, let me write it this way. F net has to be slightly greater than the centripetal acceleration that you would expect. Like you would find the centripetal acceleration has magnitude v squared over r. So whatever v squared over r is times its mass, the force that's applied to the mass has to be just slightly greater so not only does it continue moving in a circle, it's also pulled towards the center just a little bit. Otherwise, it would just happily move in a circle forever, right? So we can calculate the work that's done. The work done by this, or the net work done on the mass, an integral from 0 to r. I'm actually just going to not call that. I'm just going to call it F net. We know that the F net has to point slightly towards the center. Yeah, it's pulled towards the center of the circle. So think of it this way. You have to apply a force just to get it to move in a circle to begin with. In order to get it to move in an ever decreasing in size circle, you have to pull it with just slightly more than that so that it continues moving in a circle, but the circle is of decreasing size. So it kind of spirals in. So the work done would just be F net dot dl. So let's think about these forces. So dl, the motion of the mass, points towards the center of the circle. Like the path that the mass takes, the mass takes is pointing towards the center. This force here, the net force, should be in the same direction as dl. And that has to be the case because that's the direction we want the object to move in, right? imagine you're pulling it towards the center, so the force is towards the center. And we're integrating from 0 to r because that's the distance that the object covers as it goes from the outside of the circle to the inside of the circle. That's the distance that it travels. So what this implies, that those two facts combined means that fnet.dl is greater than 0 because they point in the same direction. Any two vectors that point in the same direction, if you take their dot product, they give you something that's greater than 0. And we then just integrate. So this is just a number now, or it's a function that's strictly greater than 0. We integrate that from 0 to some positive number. And so it spits out that the work done is greater than 0. So the change in kinetic energy is greater than 0, as expected. So it makes sense that the change in kinetic energy is positive because there is indeed some work that's done. Now, this can be a relatively more complicated example. So we're going to do this type of problem again, but in a simpler case. So a simpler example is, imagine you just have like a table with a hole in the middle. And through that hole, you put a string. And the string comes out. And you just tie like a rock to the end. Some mass m. And you just start that, and imagine it's frictionless and all that business. And you just start that mass going around in a circle. Now, in order to get it to go around in a circle, again, there needs to be some sort of inward pulling force. Let's say that this initial distance is Ri. There needs to be some tension force applied to the string so that the mass has the appropriate centripetal acceleration to go in a circle with some speed. However, if you increased the tension, if you pulled down here slightly harder than you needed to in order to get it going in a circle, this would be much the same as what the ice skater is doing, right? It would apply a slightly greater force than is necessary to keep it going in a circle, so its circle will start to decrease in size and it will end up at some smaller radius. So maybe it's then swinging around at some smaller radius because you pulled it down. Erase, will you? Oh, and it has some initial angular velocity, some final angular velocity, whatever that may be. So is the m at, yeah, it's like a point mass tied to the end of the rope. And like, just imagine like someone's pulling on the other end of the rope below the table or something. So this is a sufficiently simple example that we can actually find the work done when the distance from the block to the hole changes in this way. So let's do that. So the first method is we're just going to do the integral. And by the way, hopefully you guys can see why this is analogous to the ice skater. We're just simplifying it dramatically. So the first method is just, we're just going to do the integral and find the work. So before we can do that, in order to get the mass to change its circle size very, very slowly, of course, we need that Fnet is, again, as before, slightly greater. I'm going to put slightly above here. Slightly greater than m times v squared over r. That just has to be the case, because if it weren't, then it would just move happily in a circle, right? And we don't want it to be too much bigger, because if it were, not only would it move in a circle, it would also acquire some radial component to its velocity. So it would just, like, imagine pulling extra hard. Instead of going around in a circle, it would just come towards the center, which we don't want. We want its motion to remain circular, but have decreasing size. So what we really want, So what we can do is, if we want to find the work done, let's just find the work done as if these two were actually equal. And then we'll know that the work done is infinitesimally small or infinitesimally greater than what we calculate, i.e., it's the minimum amount of work that you can do to make this happen is how much we're going to calculate. So let me just get on with it. So the work from I to f is an integral from radius I to radius f of f net dot dl. Now again, dl points towards the center of the circle. F net also points towards the center of the circle. So we can do this. This is just so this we know that f net dot dl should point again should be positive. But what's about to happen, I'll explain it. So we want to write this in terms of the radial, we want to write it in terms of the radial coordinate r. And so the dl vector actually points in the negative dr direction. So what we really have is we have f net times negative dr. Now, even though it looks like this is going to work out to be negative, what we find is that in these coordinates, Ri is greater than Rf. So this is still positive, and this is still positive, because while we have a negative sign built in there, we have a larger number in the bottom slot for the integral. So the whole thing will work out to be positive, I promise. As it should be, right? Right, so now we can just do an integral. This is just an integral that we can just do. Well, actually not yet, we're almost there. So gonna pull out a negative sign, we have an Ri here. Actually, you know what I'll do? Yeah, I'll do it this way, just so it tracks with my notes. Now we know that the F net has to be slightly greater than MA. So I'm just gonna say that it's equal to MA, because this will tell us the minimum possible value of the work that could be done. Now A, there's two formulas for A, right? One of them is V squared over R. Another one, you might recall, is R times omega squared, right? They're the same thing. And so we want to use that one because the linear velocity is not particularly relevant here. Angular velocity is. Because that's the direct, so the circle, or so the direction of motion is towards the center, which the vector R, let me just write it this way. This is equal to F net times negative, or times dr. Well, how do I want to write this? So the vector dl points in the negative r direction, where r points from the center outwards. So that's why I did that. Hopefully that makes sense. Okay. Right, so let's do that substitution. So we have m times, let me just put it all in parentheses, mr omega squared dr. Now the important point is that omega is not a constant here. Omega is changing as the radius changes. It's changing in speed. But what we can do is we can factor out the m at least. So we have ri to rf, r, or omega squared r. Now, again, omega is not a constant, so we can't pull it out, and you guys need to be careful when you handle problems like this for that reason. So now we're going to stop with doing this integral because we don't know what omega is. We need to know what omega is in terms of its position. So omega, the speed that it's going around with, is going to change as it gets closer and closer to the center. We need to know exactly how it changes. We need a formula for omega in terms of the position, or the radius r. So the important thing to note here is that the force that we apply does no torque, or produces no torque. And the reason for that is it's a central force, like we talked about on Wednesday. No torque around the pivot. And the pivot being located in the center, of course. So what this implies, it implies that the angular momentum is conserved. So you can see why angular momentum conservation is super useful. So if angular momentum is conserved, that means that I omega, whatever it is, at any point in time is a constant. It's just a number, and it doesn't change with time or with position. So what that means is we can write the angular momentum, the total angular momentum at, say, when the mass is some distance r away from the center. That would be mr squared times omega, and I'm going to put an of r there. It's not multiplied by, it's just of r. I'll actually just leave it as omega, but that is the omega at position r. And that has to be equal to the initial angular momentum because it's conserved. So this would be mri squared omega I, right? The initial angular momentum is mr, or the initial moment of inertia is mr squared. The initial angular speed is omega sub I. And because it's constant, we can write the angular momentum at any distance r in terms of the angular momentum, the initial angular momentum. And so what this means is we can solve for omega as a function of r just by dividing through by this stuff, right? So omega, we learn how omega varies with the radius. So as the radius increases, omega decreases, and vice versa. So now that we know how omega varies, we can plug that in there. Now we know that the work done as it goes from I to F is negative m times integral from Ri to Rf times the integral, or times, not times the integral. So we want to plug in omega squared, which is Ri over R squared omega I, and then that whole thing is squared times R dr, right? I just substituted in what omega is as a function of R. And so we can rewrite this. This is m times Ri to the fourth omega I squared times the integral from Ri to Rf of dr over R cubed, right? And so we can do this integral, and we're left with 1/2 mri squared omega I squared times Ri squared divided by Rf squared minus 1. So this is our total work that's done. Now, let's just double check and make sure that it makes sense. We know that the work done should be positive. So all of these first coefficients are positive. Just need to check that the parenthesis is positive. Now, Ri is the initial radius, the initial distance. Rf is the final distance. So Ri divided by Rf, let me actually move this down so you can see it better. Ri divided by Rf is a number that's greater than 1. And it has to be because, you know, I mean, it's Ri is further out than Rf. So Ri squared minus divided by Rf squared, also greater than 1. So when we subtract off 1, we get a positive number. So this whole thing is positive, as expected. So while it looked negative for some time, it's because of this Ri was in the bottom. This is remember the standard calculus fact that if you have like 3 to 5 f of x dx, this is equal to negative 5 to 3 f of x dx. So this negative sign and the fact that Ri was on the bottom kind of went hand in hand to make this thing positive again. That was the point I was harping on earlier. Okay, so that's how we could do that. We could find the change in kinetic energy this way. But there's another way, slightly easier, which just uses the work energy theorem. THM theorem. So the work energy theorem tells us that the external work done should be equal to the chain. Yeah, so I just used, so this is angular momentum conservation. So I just used the fact that the angular momentum is always constant, that I times omega has to be constant. And then I just wrote out what I is as a function of R and what omega is as a function of R. And then I multiplied them because that's the angular momentum. And then I noted that because it's constant, that combination of terms has to be equal to the same combination of terms in the initial state. when the initial position, or when the distance was Ri and the angular velocity was omega I. Then I just set them equal because they're both the same number, they're both constant, and solve for omega of R. Hopefully that makes sense. All right, so the next thing that we can do is we can apply the work energy theorem, which basically just says the external work done, in this case the work done by this pulling force, should be equal to the change in kinetic energy. Now the change in kinetic energy, this is a rotating system, so we can just use final minus initial rotational kinetic energy, 1/2 IF omega F squared minus 1/2 II omega I squared, right? So we know what IF and II are. IF, well, it's just m times r squared, where r is Rf. So this is mRf squared times omega F squared minus 1/2 m times Ri squared times omega I squared. Remember, the moment of inertia for a point mass, this is just always true, about any pivot point, wherever it is always just the mass times the distance from the point mass squared to the pivot point. Now, again, we're going to use the fact that angular momentum is conserved for the same reason as we described above. And so what that implies is we're just going to use this fact that omega of r is equal to Ri squared, or Ri over r squared times omega I. And so we can just plug in r equals Rf. So omega F is equal to, just plug in r equals Rf, Ri over Rf squared omega I. And that's the final angular velocity. And so we can take that and we can plug it in. So what we end up with is after doing some simplification, that the work done is 1/2 times mRi squared omega I squared times Ri squared over Rf squared minus 1. And again, looking above, you'll see that it precisely checks out with what we just with what we did using the work or by doing the integral for work. It's the exact same formula, which is really a good thing because it's a theorem, so it should always be true. So there were two ways that we could do this. We could actually calculate the work done by an integral, or we could just use the work energy theorem, which is also generally true. So the whole takeaway from this process of calculating these, like the work done, is that sometimes problems that might seem otherwise hard, like how would you compute the work done with this without having any sort of, like if you didn't know what angular momentum conservation was, doing this method in either of these, or doing either of these methods wouldn't work, right? You wouldn't know what omega sub f is or what omega as a function of r is. So the fact that we have that kind of gives us a lesson, and the lesson is just thus: any situation that involves only forces that emanate from a single point or point towards a single point, any situation that only involves central forces, conserve angular momentum about that point, and you can use that to learn a lot. And in fact, one thing that we can learn, one thing in particular, is that there are some forces, or there are some problems that can only be solved with angular momentum conservation, at least at the level that we're at. And that's because they involve external forces that kind of break translational momentum, right? So like you can have, how do I want to phrase this? There are situations where you can have angular momentum conservation without having translational momentum conservation. And one way that you can have that is if you have external forces such that those external forces don't cancel or don't give you net zero force, then translational momentum is broken. Translational momentum conservation is broken. However, if that net force points towards a central point, well, then you're in luck, because then you don't have to worry about angular momentum not being conserved. It just is, because central forces produce no torque. So I'm going to give you an example. of a case where we can use angular momentum conservation, but we can't use translational momentum conservation. So this is another type, or another more complicated version, of a ballistic pendulum. Pendulum. That sounds wrong. Pendulum sounds better. So here's the picture. So instead of a string hanging from the ceiling with like just a block underneath it, we have like a ruler attached to a hinge on the ceiling. Maybe that ruler has a center of mass in the middle, and you fire a bullet at it. Now, the ruler initially is not rotating. It has some moment of inertia about the end. I'm gonna write I sub end. This is 1/3 m times L squared. Remember back when we talked about moments of inertia of a rod, this is the moment of inertia of a rod about one end, right? Now, let's consider for a moment what forces are at play once the bullet hits the ruler, the rod. Well, so if it wasn't connected at the top, the rod would just go off, right? It would just go off into the distance. It would rotate some, but it would like just move. So that means that there must be a force keeping the rod attached to the ceiling that just makes it swing instead of just going. And so we can look at what that force would be, where we would be applying a force to the bottom of the rod, to the right. So that means that there must be an equal and opposite force that prevents it from moving. Maybe not equal because, you know, the center of mass might move, but there should be some force on the top that prevents the whole thing from moving. So there is a force acting on this rod that points to the left, is what it boils down to, right? That just has to be the case. But the whole method that we used to solve the ballistic pendulum in the past was we assumed that the only forces present on the block was a tension force that was perpendicular to the block, and so that force didn't break angular momentum conservation because we only there's a tension force that pointed upward and a gravitational force that pointed downward, and as long as we only wanted translational momentum conservation horizontally, we didn't have to worry about those forces because those forces wouldn't affect translational momentum conservation in the horizontal direction. But here, there very much is a force that points to the left. Just has to be the case. Otherwise, the whole thing would go flying. So we can't use angular or translational momentum conservation. However, what we can do is we can use as our pivot point the hinge. And if we do that, we note that even though there is a force there, an external force to our system, that external force applies zero torque because that force is at the position of the hinge, i.e. when you do R cross F to find the torque, the R is zero. So the net torque from that force is zero, and hence you have angular momentum conservation. So we can use angular momentum conservation to solve this problem rather than translational momentum conservation. So let me just draw this out really quick. So then after the collision, it happens sufficiently fast, the bullet's buried in the bottom, and then it starts to swing, and then we do the standard thing where the rod swings upward. And now the center of mass, I drew this kind of poorly, but the center of mass should be lifted up slightly because it swings up, right? And the bullet's still down here. But at the top of its swing, oh, let me fill in the gap here. This is swinging with some angular velocity, omega. At the top of its swing, it would have angular velocity 0. And another important fact is that the bullet will have swung up a distance h. Again, I drew this poorly, but hopefully you can understand why. If the center of mass, which is halfway up, swings h/2 units up, then the bullet will swing h units up, right? That's just because similar triangles and all that. So let's use angular momentum to try to solve this problem. So first, let's figure out what the total moment of inertia is about this end. So the total moment of inertia about the hinge in both the during and after case would be, well, it's the moment of inertia of the rod plus the moment of inertia of the bullet. And if we treat the bullet like a point mass, that's just the moment of inertia of a point mass at distance L away from the axis of rotation. So in fact, this is just 1/3 times m, where m is the mass of the rod, plus little m times L squared. So this term, ml squared, that's just the moment of inertia of the bullet. The 1/3 ml squared, that is the moment of inertia of the rod, about 1m. Okay, so we've hopefully I've already justified to you why it's reasonable to suspect that angular momentum is conserved. And if you still don't believe me, consider what are the external forces? Well, there's gravity, but gravity, at least in the before to during phase, gravity points parallel. So gravity points downwards, and the radial vector, the vector that points from the hinge to where the force is applied, also points downwards. So in that case, gravity produces no torque. The other force, the only other force that's present, that's external to the system, is the force on the hinge. That's some sort of force that points either left or right or up or down or whatever, but regardless of which direction it points, this has mass m, the bullet has mass little m. Whatever direction that force on the hinge points, it produces zero torque because the force is at the pivot point. So that would imply that the angular momentum is conserved. And so we can write what the initial angular momentum is. Initially, the angular momentum is just m times v times L. Remember, this is the angular momentum of just the bullet before it hits the rod. So the angular momentum of a translationally moving object is just, and we covered this on Wednesday, it's just the momentum, mv. No, it's not supposed to be 1/3 m plus m, no. The momentum, you just multiply the momentum by the distance, the perpendicular distance between the trajectory of the bullet, or the trajectory of the object, and the hinge. And so that distance is L. So this is the R perp. This is the momentum of the object, and we just multiply them together to get the initial angular momentum. Now the final angular momentum, we can write in a different way. This is the during angular momentum. So angular momentum is conserved, they are equal. So now the whole thing's swinging. So the smarter way to write angular momentum would be I times omega. We know what the total moment of inertia is, 1/3 m plus little m L squared, and then we multiply it by the speed it's rotating at, omega. Okay, that is our angular momentum conservation equation. And so we can solve for omega, which is what we want to do. This is 3m, 3 little m over capital M plus 3 little m times v over L. So that is our initial angular speed after the bullet hits the rod. Now, again, there's no external work done because this torque here is not doing any, there's no torque from that force. Or rather, we're actually interested in whether or not there's any work done, external work done during those phases. Now, the only forces during these phases are either the forces up top, which don't produce motion, so there's no work done, and they don't produce torque, so we don't have to worry about rotation. And then there's gravity. So we can just put the Earth as part of our system as we typically do, call that a potential energy. The contact force doesn't do anything because it's perpendicular to the path of motion. So we can just write down initial kinetic energy equals final potential energy, because there's no kinetic energy at the end of the day. There's no potential energy at the beginning of the day. So I'll write that down, and then we can then I'll answer questions if there are any. Although actually we still have more to go. Oh, a little bit more to go. So energy conservation, again, change in potential plus change in kinetic equals 0 because there's no external works here. And so we can just separate that into kinetic energy initial equals potential energy final. So let's write down the initial kinetic energy. So it's 1/2. Now this is rotational motion. So we want to talk about we want to phrase the kinetic energy in terms of its rotational motion. So it's I times omega squared. So the first term is 1/3, or the I is 1/3 m plus little m L squared. That's the I. It's the moment of inertia of the system. And then the velocity, the angular velocity squared, well, we just plug that in there. So this would be 3m divided by m plus 3 little m squared times v over L squared. Okay, so this is the initial kinetic energy. Now, just as a note, the initial potential energy, we can just choose it to be 0. We can just say y equals 0, or we can just, the potential energy you can always add a constant to as long as you're consistent. So the initial potential energy we'll just call it 0. And then the final potential energy will just be the potential energy of these things as if they've only raised that distance. Can be set to 0. All right, let's do the final potential energy. So there are two parts to the potential energy. The first part is that the whole rod, the center of mass of the whole rod has gone up slightly, right? Like it's rotated. So like if it had rotated all the way, its center of mass would have increased a lot, but it's rotated just a little bit. So the potential energy gain of the rod is capital M times G times H over 2, because the center of mass of the rod increased its height by H over 2. The bullet also gained some potential energy. It gained a height of H, and so its potential energy gain is just mgh, little mgh. And so we can factor that and write it as 1/2 capital M plus little m gh. Okay. So this is final potential energy. And here's a note that the kinetic energy is 0. By the way, the reason for that is because we're trying to find the height that it swings up to in terms of its initial velocity and so on. And so the maximum height that it gets to will be the place where it stops moving. All right, so then we just do some algebra. So after some simplification, we're left with the following formula: capital M plus 3m over 3 times L squared omega squared want to make sure that I'm not. And then I'm so I don't know why I left it this way. Let's just call it V over L squared. There. Equals M plus 2m gh. And so then we can solve for h. All I'm doing is I'm solving this equation for h in terms of all the other variables. So this is 3 times little m squared times v squared divided by capital M plus 3 times little m times capital M times 2 plus little m times g. So it's a lot of work, but we end up with an answer just by using angular momentum conservation and energy conservation. And so if we knew the initial speed of the bullet, if we knew the various masses, we could just calculate explicitly what how high it goes, how high the bullet swings up. So this exercise, like I know it's complicated, I know this is tricky and it'll take practice, and I believe that I have a problem similar to this on the homework, so keep that in mind. I can talk about that after lecture, but I just want to say one little thing, and there is there's this business with these tools, angular momentum conservation, energy conservation, and translational momentum conservation, can let us actually handle more complicated collisions now. Because imagine for a moment, you just had the rod freely floating in space, and you just shot a bullet at the bottom. Well, in that case, angular momentum is of course conserved. There are no external forces, and so there's no external torques. But also translational momentum is also conserved, and energy is conserved. So you'd need to use all three of those, but then you could see what happens as the rod starts to spin because the bullet lodges itself in it and it moves and it and like it can become a complicated problem, but we now have the tools for it. There is one point of caution, though, that I would grant you when talking about these things that are called off-center collisions. And that's when you calculate the angular momentum during these collisions, you have to make sure that the reference point that you pick to compute these things, like for torques and for moments of inertia and things like that, you always have to choose the same reference point before and after the collision. Like they have to be in the same spot, because angular momentum is only conserved if you consistently use the same reference point. So it is for that reason that you need to be careful when you do this, that you didn't really have to worry about when we were just talking about regular 2D collisions where it wasn't off-center. All right, so I'm going to end lecture there, but I will answer Cole's question.